So here we're going to talk about linear independence and this idea of, in the section in general, spanning sets. So we'll start with linear independence in abstract vector spaces. Now, we've already discussed this idea of linear independence, but this was all in relation with our Euclidean space, right? So we had this idea of linear independence as a solution here, all right, as a linear relation here. So, excuse me, sorry, let me gather my thoughts here. So when we're dealing with column vectors, right, we define this idea of a relation of linear dependence. And then we define linear independence, right, as the linear combination of those vectors set equal to the zero vector. Right? And we define here, so here, like alpha 1, u1, alpha 2, u2, plus alpha n, u to the n, equal to the zero vector, right? And when we thought of these vectors, we thought like the classical kind of thinking of a vector as some column vector in our Euclidean n space, right? And we tried to solve for these coefficients, alpha 1 to alpha n, right? And the zero vector was just a column vector filled with zeros, right? So we set up some homogeneous linear system of equations that had alpha 1 through alpha n as the variables that we were trying to solve for. Now, if only the trivial solution existed, right? Again, because this will always have a solution, right? If alpha 1 through alpha n were all zero, that would make the statement true, right? But that's not, right? That's just part of the question, right? That's what's called the trivial solution, right? Alpha 1 equal to alpha 2 is equal to equal to zero. This is the trivial solution. All right, now this will always work, okay? The question is there any other solution, right? And that's when we try to solve that homogeneous system of equations, right? In alpha 1, alpha 2 through alpha n, all right? And again, there we develop a bunch of different theorems or ways that we can describe this idea here, right? Through linear independence, a non-singular matrix, etc. Right? Now, the goal is if we only have the trivial solution, then it's Li, linearly independent, right? If we have other solutions, right? So if there is more than a trivial solution, then it has infinite solutions, right? The choices are no solution, one solution, a unique solution, or infinite number of solutions. Other solutions, infinity. Then we have linear dependence. Okay? And again, this homogeneous system, or any homogeneous system, is always consistent, right? It's either going to be trivial solution or no solution. Trivial solution or infinite number of solutions. All right, now, in our section V, when we dealt with vector spaces, here we thought more abstractly about our relation of linear dependence, right? This relation here. Right? Because if we talk about vector spaces, well, scalar addition is properly defined, and so is vector addition, right? And the sum of any vectors in a vector space will result in another vector, right? So this relation here that we've set up of linear dependence, right, is not bound to just be Euclidean to the Euclidean space, right? If the vectors, now thinking of vectors as just objects from some vector space, right, this relation still holds, right? I don't need to adjust any of my definitions. The only thing I need to clarify is that, well, I'm no longer just in R to the n, right? In fact, I just do any V, right, where we have vector space. Okay, now here is, if we make that distinction here, then that's all we really need to change, right? So here, let me switch over to our textbook here so we can see what the book has in terms of the definition. Now again, notice the definition is exactly the same. The only thing here that is going to change is that these come from just some vector space V and not R to the n or C to the n, whatever if we're dealing with complex numbers as well. Right, so here I'm reading definition RLD, relation of linear dependence. So it says, suppose that V is a vector space given a set of vectors S, right, U1 through UN. An equation of the form, again, right, same as before, alpha 1 vector U, alpha n, vector U sub n is equal to the 0 vector, is a relation of linear dependence. All right, so exactly the same. The only thing here is now the scalar multiplication and the vector themselves, they are representing, right, just abstract objects. Maybe it is a column vector, maybe it's a polynomial, maybe it's a matrix. All right, and this idea of linear independence, right, also exactly the same here. Suppose that V is a vector space. The set of vectors U1 through UN from V is linearly independent. If there is a relation of linear dependence on S that is not trivial, right, in other words, more than one solution exists, in the case where the only relation of linear dependence on S is the trivial one, then S is linearly independent set of vectors. All right, again, only is the key word there, right? If we just show that the 0 solution is a solution, that does not give me any information in linear dependence and linear dependence, right? We need to show it's the only solution for linear independence. Okay, so a couple of things to think of here when we are dealing with this definition here, right? Again, as always, right, these vectors, right, think of them as objects from a vector space, V. Okay, so maybe it is a column vector, right? A1, AN. Maybe it's some kind of polynomial. Maybe it's some kind of matrix, right? It's an object, right? And whatever vector space we're coming from, right, we use the appropriate scalar multiplication and vector addition, right? Which again, we know they are closed under those two operations because it is a vector space. Okay, and then also the 0 vector, right? 0 vector, right? This depends on what vector space I'm working with, right? Okay. So maybe it is the column vector of zeros. Maybe it's the 0 polynomial, maybe it's the 0 matrix, right, of whatever size of the vector space that we're working with. Okay, so here's how it would work here, right? So here I'll just set up our equations here. So let's say that S is equal to the set 2 plus x minus 3x squared minus 8x cubed, 1 plus x squared plus 5x cubed, and then 3 minus 4x squared minus 7x cubed. Okay, and I want to determine if this is S linearly independent. Okay, so what I would do here, again, I have 3 vectors here. All right, so 3 vectors. here. Okay, so I would set up here. So I'll call this one like U1, U2, and U3. So my alpha 1, U1, plus alpha 2, U2, plus alpha 3, U3, equal to the 0 vector. All right, since here we'll assume that S is a subset of P3, right? All polynomials up to and including polynomials of degree 3. So again, the standard definition of it, so our 0 vector there is this. Okay, so here we have alpha 1 times 2 plus x minus 3 x squared minus 8x cubed plus alpha 2, 1 plus x squared plus 5x cubed, and then plus alpha 3 times 3 minus 4x squared minus 7x cubed equals to 0. All right, and the idea here, all right, so what you'll do is you'll multiply and then combine the collect the like terms, right? So all the constants, right? So looking here, be 2, 1, 3. So 2 alpha 1 plus alpha 2 plus 3 alpha 3. All right, and now my linear terms. So x, so that's alpha 1, x alpha 2. All right, and then here there's no linear term in this polynomial here, so that gives me my x. And now moving to the square term, so that's minus 3. So minus 3 alpha 1 plus alpha 2, and then minus 4 alpha 3. That's x squared. And then lastly, my x cubed, we get negative 8 alpha 1. Okay, and then plus 5 alpha 3. Oh, excuse me, 5 alpha 2, and then minus 7 alpha 3. All of that equal to 0. Oh, x cubed, and then all of that equals to 0. Okay. All right. Okay, and then now from here, right, we want to, don't worry about the x, right? X is a variable. Sure, we can find values of x that will make this 0, but that's not what we're after, right? X can be any real number. It's a polynomial. What I have control over here are the coefficients, right? So what I would do here, my linear system will be 2 alpha 1 plus alpha 2 plus 3 alpha 3. That equals to 0. And so with the next coefficient, 3 alpha 1 plus, alpha 1 plus alpha 2 and then negative 3 alpha 1 plus alpha 2 minus 4 alpha 3 equals to 0. And then here, minus 8 plus 5 minus 8 alpha 1 plus 5 alpha 2 minus 7 alpha 3 equals to 0. All right, and then from here, right, you could set up your equation here, 2, 1, negative 3, 8, and then in alpha 2 here, we'll have 1, 1, 1, 5, that's negative 8, alpha 3, we got 3, 0, negative 4, and negative 7. Okay, All right, and again, since it's a homogeneous system, I don't worry about the augmented part. So you would work through that, right? You would solve this RREF, right? And then from there, you would determine all these strategies, right, we've covered before, right? The only thing new here is that here we start with vectors being, in this case, polynomials. But nothing changes, right? This all works the same, right? So for example, let's say here S is the set 2, -1, 1, 3, 0, 4, -1, 2, and then 4, 2, 1, 3. And S is a subset of 2 by 2 matrices. Is S linearly independent? Right, again, right, think abstractly, right? We refer back to our definition here of linear dependence, the relation of linear dependence. Right, this here, that remains the same throughout, right? How I define the scalar operation, the scalar multiplication, and the vector addition, that is dependent on what vector space I'm in, but the formulas themselves are unchanged, right? Here, now this is my vector. So we could say, is S linearly independent? Well, let me find out, right? I would do this. Okay, so be alpha 1 times 2, -1, 1, 3, plus alpha 2 times 0, 4, -1, 2, plus alpha 3 times 4, 2, 1, 3, equal to the 0 vector, which here, again, unless specified otherwise, it's the standard operations of scalar multiplication of matrices and addition of matrices. So our vector, the 0 vector here, would be the matrix of all zeros. And again, here what we would have is, right, using scalar multiplication, we get 2 alpha 1, 0 for alpha 2 in this position, plus 4 alpha 3. Excuse me. Okay, and then here, what do we have here? Negative alpha 1 plus 4 alpha 2 plus 2 alpha 3 in this position. Then in the second row, first column, we got alpha 1 minus alpha 2 plus alpha 3. And lastly here we got 3 alpha 1 plus 2 alpha 2 plus 3 alpha 3. All of that equal to my 0 matrix. And now again, right, what do we have? We have a system in 3 variables, 4 equations, and each one of them we set equal to 0. 4 alpha 3 3 alpha 1 plus 2 alpha 2 plus 3 alpha 3 equals to 0. And I try to solve this homogeneous system, right? Again, I know that the 0 solution exists, right? That's not the question being asked here, right? The question is the trivial solution the only solution that exists, right? So here we'll have 2, -1, 1, 3, 0, 4, -1, 2. We have 4, 2, 1, 3. All right, and then again, we'll proceed as before, right? Once we're here, this is a problem that we've had at this point solved many different times. All right, so all those techniques still are valid, right? How we interpret the results, those are the same as well. Okay, so just keep that in mind, right? Here, what we're doing is we're thinking just more abstractly here, right? This idea of linear independence is not something that only is valid for column vectors. Okay, it is valid for any objects that are coming from vector spaces. Okay, all right. Think so. The next thing we're going to do here in the next video is we're going to talk about this idea of a spanning set, right, and the uniqueness of the representation of that spanning set.